Hello and welcome to the course Design Bore Fields with Confidence. This is the third chapter of the sixth part and we will be looking at the GEROtherm VARIO and FLUX probes from HakaGerodur. Now these VARIO and FLUX probes, they have a conical design. And by that I mean that the wall thickness is not constant over the pipe length, but it's a little bit smaller near the surface than it is at the bottom. And the reason for that is that if you have a slightly smaller wall thickness, your inner diameter will be a little bit bigger, and so your pressure drop will be on average lower for this conical design. But the important thing is that your pressure rating still is the same, because your PN16, your PN20, 30 and so forth, you only need it basically at the bottom of your borehole where your static pressure is actually the highest. So by having this conical design and still having the same pressure rating near the bottom of your borehole, your probe will have the overall same pressure rating. Now, how do you develop a model for such an innovative probe? And we do that by dividing the probe in basically three regions. Now, the VARIO and FLUX probe, they are both conical, but they have different names because they have different applications and different depths they can reach. But conceptually, there is always a first part in which the wall thickness is constant. Then there is a certain point at which the conical region starts and the wall thickness increases linearly with depth. And then for some probes there is also another third region in which you have again a constant wall thickness, but now a little bit thicker than at the top. And the regions for which there is a constant wall thickness, we know the solutions for that. It's only basically for this conical part that we need to develop a new solution. Now, a first idea might be just take the average value and take the average wall thickness between the top and the bottom, and we're done. Now, the problem with that simplified approach is that the parameters of interest, our Reynolds number, our friction factor, our pressure drop, and our effective borehole thermal resistance, they're absolutely not linear with the wall thickness. And just to illustrate that, and a full mathematical explanation is again in a textbook, the Reynolds number, as you know, it's a function of the internal diameter, as well as your flow velocity in meters per second. But this flow velocity in turn is also a function of the inner diameter. So it's absolutely non-linear, and the Reynolds number is even the most simple of all the parameters we're actually interested in. So we cannot simply take an average value for the wall thickness and assume we're done. So we have to rely on a more intelligent approach, let's say, and that's the mean value theory. And it looks like the formula here below, but it's more clear if we just look at a graphical explanation of this. So here we have our red curve, which is the curve of interest, and we want to calculate the average value between points A and B. Now in the simplified approach, what you would do is you basically draw a straight line between the value at A, the value at B, and take the middle value of that. But that's not the best thing we can do. So the approach here is that we take the integral of this curve, we sum basically the area between A and B under the red line, and then we search for a rectangle with the base B minus A that has the same area. So by doing so, we convert this irregular area to a rectangle, and by taking the height of this rectangle, we actually find the average value. And just to show that this makes actually a difference, let us take a look at the Reynolds number for different lengths alongside the conical part. And as you can see, the average value versus the mean value theorem, it diverges towards the end. Now, the difference might not seem that big, but what is important is that these probes, especially the flux probe, they are designed for 300, 400, 500 meters borehole depth. And there, the even small differences can play a big influence in the end, especially when we're working in this transient zone between laminar and turbulent flow. So by using this mean value theorem, we can find the actual values for the Reynolds number, the friction factor, the borehole resistance, and so forth. So let us now take a look at how this all relates to the effective borehole thermal resistance and the pressure drop again. So here we revisit once again what we talked about in the previous part in the first chapter, and compare the single versus the double U-tube from a thermal perspective. And here you see that there is not a lot of difference between the Vario single and the Vario double for the same PN16DM32 probe. The only thing you can see is that on average in the laminar and in the turbulent region, our Vario or conical probe is performing a little bit better. And the reason for that is that our wall thickness on average is a little bit smaller. So meaning that our pipe resistance, the resistance for the heat conduction to the pipe, is also a little bit smaller in our conical probes than it is in our regular pipes where the wall thickness is constant. Now the second thing you can notice here is that where the regular probes, they have a sharp cutoff between laminar and transient regime, here that's not the case. And that's again due to this conical design, because part of the probe can be already in the turbulent regime, can have a Reynolds number higher than 2300, but the other part of the conical section, not. Because there the inner diameter is a little bit bigger, so you need a little bit higher flow rate to transition to turbulence. So basically for this conical probes, and the same holds for the flux probe in a second, is that you need a slightly higher flow rate to get the whole pipe in a transient regime. Whereas with the regular design where you have a constant wall thickness, it's just at one flow rate where the whole pipe transitions. So that's why the jump between laminar and transient is a little bit more smooth in the case of the Vario probe. Now, as said, these Vario and flux probes, they are actually designed with deeper boreholes in mind. So let us take a look at the case with a flux probe, actually at 350 meters deep now instead of 100. And what you see here is a very different graph. First of all, the effective borehole thermal resistance, the range is way bigger. Now, the detailed mathematical explanation for that is over in the textbook. It's not so important, because when you have these type of drilling depths, basically your flow rate is also rather high. And if you compare the flow rate of 0.2 liters per second, for example, in the previous graph, which was for 100 meter, logically, you will need 0.7 liters per second in this graph just to keep the flow rate per meter borehole length constant. So just keep that in mind. We're mostly looking at the right side of the graph here. And if you then compare a single and double DN43, PN32, it's a conceptual, a theoretical model, what you see here is that our flux probes are performing better thermally than our constant single probe, and because the same reason, the wall thickness is on average a little bit smaller. And we also see that our single flux DN53, so an even larger diameter, it comes really close to the performance of the double DN43 here. It's still a little bit underperforming in the turbulent region, but it's very close. And if you look at the pressure drop in a second, it will actually be an interesting trade-off there. But again, here we see that within certain flow range, for example 0.3 liters per second to 0.5 liters per second, our single flux actually outperforms the double DN43, also from a thermal perspective. So this is just to show how different pipe diameters, again, as we discussed already a couple of times in this part as well, play a role in determining when a certain solution would be better than the other. But let us now take a closer look at the pressure drop, because that's actually where this probe was designed for. And there the solution, or the difference, or the value is clearly visible. Because here, if we just compare again the Vario DN32 PN16 with the regular probes, you see that for the pressure drop perspective, it's always better. And this is again due to the fact that you have, on average, a smaller wall thickness, meaning that also your pressure drop will be lower. And this is even more pronounced when we go to the deeper boreholes at 350 meters in this case, where the single DN43, it just shoots off to very high pressure drops, and the flux DN43 is already at a way lower pressure drop, meaning that also the pump electricity consumption will be lower in this case. And what is also interesting is that our single flux DN53 has overall a lower pressure drop than our double DN43, meaning that in the thermal perspective, as we saw just 2 slides ago, the effective borehole thermal resistance from this single flux DN53 versus the double DN43 regular probe was quite close, and the double was slightly better. But from a hydraulic perspective, the flux is the clear winner in this case. It's even better than the double DN43 because of this larger internal diameter. And just to show this in a slightly other graph, instead of varying the flow rate for the same pipe depth, let us take a look at this flux DN53, but now for different borehole lengths. And we plot the two other lines, basically asymptotes, for the PN14 and PN38, which are respectively the pressure rating at the top of this flux probe and at the bottom. And what you can see is that for the first, let's say 200 meters, the pressure drop is mostly similar to the regular probe at a PN40, because basically up until 140 meters it is exactly the PN40, and then it starts increasing, but it increases rather slow. So it takes a couple of extra borehole meters in order to see the deviation away from the regular PN14 probe, and after a while it starts running in parallel with the PN38 probe. But what is important is that when you say I want a pipe with a pressure rating of PN38, if you have the flux probe instead, you will have a lower pressure drop across the whole range of borehole depths and as well as flow rates. So this was what I wanted to say about the GEROtherm VARIO and FLUX probes. I hope you found this interesting. Try it out in GHGTool for your perhaps deeper borehole projects and see how the pressure drop and the pump electricity consumption change when you go from a regular probe towards a conical one.